Welcome everyone. We are now on the 6.0 tutorial examples. So I'm going to help you tackle the 6.0 tutorials. Now, these tutorials, if you do them, you will be very good. You will probably be as well off as I am in understanding momentum and how it relates to forces over a period of time. Okay? And how you kind of blend that together with energy. All right, so let's get started. Let's go ahead and go with our first example. I think you also have one where there is a constant force. So here we go. It says we have a 2 kilogram object that is initially moving at 10 meters per second. And then it's hit by a force given in a description in this force versus time equation. They are asking to find, they want us to find the impulse, the final velocity after the impact, complete the velocity versus time graph, find the displacement during the force, and find the total work done on the object. There's a lot of ways to do this. I've tried to give you as much tools as you can, okay? And I'll try to do each one of these a little bit different ways so you can see how to do it. For this first one, I'm probably going to spend a little bit more time than normal on this, so that way I could tell you a lot of different ways to do this. But start off like we should start off is list out your equations, your momentum equations and your energy equation. Okay. List out your variables that you have. We have a 2 kilogram object that is initially moving at 10 meters per second. We're being asked to find the final velocity. Now we do have time from the graph. You can see it takes place for 6 seconds. They're asking us to find force. Nope. They're asking us to find impulse, which in this case is going to be very easy. So try to go in order. That'll help you out in doing these. All right, so we need to find impulse first and final velocity. Well, I'm going to start off by putting our equations in. So initial momentum is going to be 2 kilograms times our initial velocity, 10 meters per second, plus impulse. And that's going to be equal to our final momentum, which is going to be 2 kilograms times the final velocity. So right here we have 2 unknowns and 1 equation. We really can't solve the problem. So solving impulse first is going to help you get the final velocity. So let's figure out what the what the impulse is. Well, the impulse is force times delta t. So if you notice, the slope of this line is 0, which is force versus time. But if you take force times time, that will be the area underneath this line. Okay, and so I'm seeing a rectangle here. So that impulse is going to be equal to force delta t, which is going to be equal to -4 newtons times 6 seconds. So that impulse of this guy is going to be, what is that, -24 newtons seconds, which is, by the way, it's -24 kilogram meter per second. So they're the same thing. Okay, so this impulse that we just figured out, we're going to toss in right here. So this is going to be 20 kilogram meters per second. Impulse, which we just found, J is going to be equal to -24 newtons seconds. So we just figured that out. So this is going to be -24 Newton seconds, but it's also kilogram meters per second. And that's equal to 2 kilograms V final. So this is going to be -4 kilogram meters per second. We divide that by 2 kilograms and we have V final. So this is going to result with a final velocity of -2 meters per second. So V final equals -2 meters per second. Okay, let's complete the velocity versus time graph. I have you do this because you could then find the displacement really quick from this. And from that, you could just calculate the total work. You don't have to put it into the kinetic energy and do it the longer way. So I'm trying to give you as many tools as you possibly can. So here it starts off moving to the right at 10 meters per second. So here's its initial velocity up there. And then over the period of 6 seconds, it's going to wind up at a -2 meters per second. So what this means is this is going to be the slope of that. Oops. Now, I can tell you it does in fact cross the line at the 5 seconds mark. Okay, so this is a good problem for the Physics 111 students to do. Okay, so to find the displacement here, you could take this area, which I'm going to outline with black, this area, and then subtract it from this area right here. Okay, so this top area right here okay, that top area is the we're going to find the displacement of that black top area right here. So that right there is a rectangle, which I'm seeing is positive 10 times 5 times 10 meters per second times 5 seconds. But since it's a triangle, which is a half a rectangle, we're going to divide that by 2. Now we have to add to that this next area right here, which is the red area, which is another rectangle, which looks like it's going to be -2 times 1 second. So that's going to be a -2 meters per second times 1 second over 2, because that's another triangle. Okay, and see how that's negative? It's going to be subtractive, which is going to be delta x. Right here, this is going to be 50 divided by 2, so that's positive 25 meters per second divided by times seconds, so that's just meters. And this is going to be a -2 divided by 2, so that's going to be divided by -1 meters. So overall, we're going to get our displacement as positive 24 meters. Okay. All right. So another way you could have done it is this change in velocity right here. This is creating an equation for this. Okay, so for my 121 students, we're going to do this above the line. So we're going to create a velocity versus time function. Okay, so it starts off, okay, and again we're doing mx plus b, and remember from motion that the area underneath the line, a velocity versus time line, that is displacement. Okay, so it starts off at positive 10 meters per second, t, right? Now the slope of this line, okay, the slope of that line, which is acceleration, is going to be, so that acceleration slope is going to be negative 2 meters per second plus, well actually, it's going to be dv, so here's what I'm doing is dv dt, that's the slope of this line. So we're going to subtract that from a positive 10 meters per second, so it's the change in velocity or change in time over the period of 6 seconds. So what we're going to get is negative 12 meters per second over 6 seconds. So that slope is negative 12 meters per second, negative 12 meters per second over 6 seconds times t. Okay, so now if we want displacement, we just have to integrate this. So from 0 to 6 seconds. So that will be negative 12 meters per second over 6 seconds, t plus 10 meters per second dt. So this is going to result in that t squared, so we'll have negative 12 meters per second over 6 seconds, t squared divided by 2, plus 10 meters per second times t from 0 to 6 seconds. So we're going to put in 6 seconds here and get a number for this first part. So that's going to be 36 divided by 2 times 12, that is negative, divided by 6 seconds. So that's negative 36. So this will be negative 36. And this is going to be meters plus 6 times 10. So that's going to be 60 meters. So that is going to be equal to positive 24 meters, delta x. So for me, I think this way we did with the triangles, I don't know, it's kind of, it could be more difficult than this sometimes. All right. Okay. Well, now that we have displacement as 24, well, we could just calculate work really quickly. So there's a couple ways to do that. Work is just force times displacement, right? So our force, which is a constant force, is a negative 4 newtons times displacement, which is going to be a positive 24 meters. So our work here is going to be 24 times 4, so that's 96. So that's going to be, which is going to be negative 96 joules. All right. So technically we have finished the problem, okay? We've figured out displacement, which is positive 24. We have work done. We have displacement. We completed the velocity versus time. So work is equal to negative 96 joules. Displacement was positive 24 meters. We could have got work, and we could have gotten work a different way, okay? We could have taken, so since the height wasn't changing, it was on flat ground, so none of the potential energies, we had initial kinetic energy plus work is equal to our final kinetic energy. So that's our problem. Now if we put in 1/2 the mass, which is 2 kilograms times the initial velocity squared, 10 meters per second squared, plus work, and put in our final velocity here, which is 2 kilograms times negative 2 meters per second squared. Was it negative 2? Yep, negative 2. Well, this is going to be 100, so this is going to be 100 joules plus work, which is going to be equal to 4 joules. So our work, if you bring this on the other side, is going to be 4 joules minus 100 joules, which is negative 96. So we could have just got the work first. And then, since work is equal to force dot delta x, and so work divided by force is equal to delta x, we could have got 96 joules, that is negative, divided by a force that is negative 4 newtons. And so 96 divided by 4 equals 24. So since those are both negative, it's now positive. So that delta x is going to be positive 24 meters. So again, there's a lot of ways to do these problems, and I want you to use tools that you're comfortable with to help you verify, but I do want you to try to stretch on these problems, okay? So please try to stretch on these problems and try to use something that you're not comfortable with, right? So if I don't feel comfortable integrating velocity versus time to find displacement, I'm going to do that, okay? Especially since I already know what the answer should be, okay? Okay, let's move on. In one of the problems, I give you a velocity versus time graph, and then I have you solve for all those things that we just solved for in the other problem, okay? So in this problem, you can kind of see that this may or may not be crossing the line at the 3-second mark, okay? So I don't trust it, okay? So what we're going to do, we're going to kind of work backwards, okay? So if we have an initial velocity and we have the mass, we could actually just start building the momentum part. So the initial, so the mass times the initial velocity, which is positive 8 meters per second, plus impulse, and I do think they want the average force, so we could assume this is a constant force in this problem. That's going to be plus impulse, which is going to be equal to the final momentum, which is the 2 kilograms times the negative 4 meters per second. And I'm going to put a negative here, negative 4 meters per second. Now for the impulse, which is J, we could actually do this. This that we're going to solve for is the average force times the whole amount of time, which is going to be 4 seconds. Okay? So since we're assuming, so in any problem that you do, the average force that you work out will be a constant force. So we're just going to go ahead and solve for that average force right now. And again, I'm trying to use whatever tools I have available to me. So this is going to be over the period of 4 seconds, which is going to be this. Okay? So this is going to be positive 16 kilogram meter per second plus the average force times 4 seconds, which is going to be equal to negative 8 meters per second. So we're going to subtract that 16 on the other side, and I should have wrote kilogram meter per second here. So when we do that, you're going to get negative 8 kilogram meters per second minus 16 kilogram meter per second. So that is going to be, what is that? Negative 24 kilogram meter per second, which we are just going to divide over 4 seconds. And that's just going to give us our average velocity. 24 divided by 4. I know that's 6. I just don't trust myself. So, which is going to be negative 6. So this is negative 6 newtons. So now we know the average force. Okay. Which we could get right here. So which we're going to just plug in right here. So that's a negative 6 meters, newtons over the period of 4 seconds. So that's it right there. So that's the average force. And then hopefully this area works out to be, well, each area is 2. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 times 2 is 24. And so coming back to this to find the impulse, impulse is the average force times time. So that is going to be just negative 6 newtons times 4 seconds, which is going to be negative 24. So Newton seconds. So that's the impulse. So we found the average force. We found the impulse. We don't need to find the final velocity after the impulse because that is given, but I suppose you could just write that down. And we completed our force versus time graph and the average force. So now we could solve for the displacement. Again, there's a lot of ways to do this. The problem with this way, finding the area underneath the line, is I don't trust that that is crossing the line at the 3 second mark. I don't think it is. Okay. And to find out, what you would do is just take that line. Well, let's find out if it does. Okay. We're going to create a velocity equation, which is going to be, it starts off at positive 8 meters per second, and it ends at negative 4. So that's the initial velocity, is positive 8. The slope of this line is going to be negative 4 meters per second minus a positive 8 meters per second over the period of 4 seconds. So that is going to be negative 12 meters per second over 4 seconds. T equal plus 8 meters per second, right? So, all right. Well, where it crosses the line at 0 seconds, we're going to call that 0 velocity. So negative 12 meters per second over the period of 4 seconds, that is going to be, multiply that by, well, that's going to be what we're solving for, plus 8 meters per second. And I should be working upwards. I'm just going to grab this real quick. That little guy. So solving this for time, we're going to have negative 8 meters per second. This is going to work out to be negative 3 meters per second squared. So that's going to be negative 3 meters per second squared, t. So negative 8 meters per second divided by negative 3 meters per second squared. That is definitely not divisible. So it doesn't cross the line, so that's 8 divided by 3. So it crosses the line just before 3. So you don't want to do this if you're, find the area underneath this if you're a Physics 111 student. The best way to do this, I think, because to figure out, we're going to figure out, and we're trying to figure out displacement, the area underneath this line is the displacement. So what I recommend if you're 111 is do it this way. You got 2 kilograms. We're going to solve for the work done first, times 8 meters per second that we're going to square. It has no change in potential energies, plus work. That's going to be equal to 1/2 times 2 kilograms times a negative 4 meters per second that we're going to square. So that stuff is going to, this is going to all work out to be 64 joules plus work, and that's going to be equal to 16 joules. So the work done is going to be 16 joules minus 64 joules, which is going to be, that's got to be a million at least. I'm just kidding. Negative 48. So the work is equal to negative 48 joules. And so now, just like the other problem, what we could do is just take force dx is equal to work and then our force we know is 6 newtons times dx. This is going to be equal to negative 48 joules. So the displacement is going to be 48 divided by 6, which is going to be 8. Okay, so we could have done it that way. If you're a Physics 121 student, if you've gone this far to create the equation right here, just integrate it, right? Integrate that equation from 0 to 4 seconds, which is going to be negative 12 meters per second over 4 seconds, t plus 8 meters per second. That is going to be, once you integrate that, that's going to be negative 3 meters per second squared divided by 2, t squared, plus 8t, and that plus looks weird. A little plus there. From 0 to 4 seconds. All right, so we got 16 divided by 2. So 16 divided by 2 is going to be 8. 8 times 3 is negative 24. 24 meters. Plus 4 was at 32 meters. And that is going to work out to be positive 8. So a lot of different ways you could do these problems. Okay. Again, if you're a 121 student, you just have more tools available to you. But if you're a 111 student, I would have done this problem this way, just with work and using work to find displacement. Okay? Okay, let's do another problem. This is a problem where our force is actually changing. Okay? So in the problem that I give you, the force line is crossing the lines at, well, if it does cross the 0 axis, it's crossing it at a whole number, like in this case 3. So I wanted to make it open for 111 and 121 students to do this. But we have two different kind of forces here. You have this force that is causing this type of motion right there. And then you have what it turns into a constant force, right? So you have a force pushing something to the right over the period of 3 seconds, Then it starts pushing it to the left over the period of 1 second. And then it continues to push it to the left at a constant force for another 2 seconds, right? And so in this case, you're given the starting values that it starts off with a mass of 2 kilograms and with an initial velocity of 5 meters per second, a positive 5 meters per second to the right. And we need to figure out all of this stuff. So we need to figure out the final velocity. It looks like we have the time again, which is going to be 6 seconds. And so we need to figure out the force. We need to figure out impulse. We need to figure out work. We need to figure out everything. So there's a lot of stuff to do here. So let's go ahead and try this out. Okay. And to do this, we're going to go ahead and start. Well, we need to start with momentum. We can't start with energy because we don't know the final velocity, and the only way I could see of getting the final velocity is from momentum because we're given a force versus time equation. So here we go. We have the initial momentum, which is going to be 2 kilograms times positive 5 meters per second. So that is going to be plus impulse, which is a non-constant value. So since it's changing, we can't use force times delta t. We can compute the average force later on, but we can't right now. And let's go ahead and find the final velocity, which is going to be, well, final momentum, which is going to be 2 kilograms, but we don't know the final velocity. So we need to actually figure out the area underneath this line, which is a couple different things. Okay, so I'm seeing a triangle there. Right? So you got a black triangle right there. Then you have this area underneath the line, which is another triangle. But then you have this other area right here. So this is, and this one is a little bit more complicated than the one you're doing, is a little bit easier in this. So, okay, so basically, let's find the areas of all of this stuff right there. Let's do this this way. So the area of the black line, which is going to be impulse, that's going to be this rectangle, which is going to be positive 12 times 3, but it's a triangle, so divided by 2. So positive 12 newtons times 3 seconds divided by 2. Now we have, so that's this first area right there. Now we have this red area, which is over the period of 1 second, and it's -4. So we're going to go plus -4 newtons times 1 second, right? So that's over times 1 second. So we're going to divide that by 2. And now we have this rectangle, right? Which takes place over the period of 2 seconds. So that's going to be plus -4 newtons times 2 seconds. So this impulse, which is a big guy here, so this is going to be what? That's 12 times 3, so 36 divided by 2. 36 divided by 2, don't know what that is. 36 divided by 2. 18. I knew that. I was just kidding. 18. So this is positive 18 Newton seconds. This is going to be -4 divided by 2, so that's going to be -2 Newton seconds. And that's going to be -8 Newton seconds. Okay? So this whole area for the whole thing is going to work out to be 8 positive 8 Newton seconds. So that is the impulse. So the impulse, positive 8 Newton seconds, right there. Okay, all the little triangles and areas. So now we're just going to insert that right into here. Okay. This is going to be positive 10 kilogram meters per second. 8 Newton seconds is 8 kilogram meters per second plus 2 kilograms V final. So this is 18 kilogram meters per second, which we're going to divide by 2 kilograms, and that's going to give us the final velocity, which is what is that? 9, positive 9 meters per second. Okay, so now we have the final velocity. While we're here, let's go ahead and fill out the velocity versus time graph. So before it's moving at positive 5, right here, and then later on it's moving at positive 9, which is right there. So this velocity versus time graph is that. And while we're here, I'm just going to put in the slope, right? So that's 1, 2, 3, 4. So that's going to be positive 4 meters per second over 6 seconds, and that is going to be the acceleration. So that's 2/3 meters per second squared. Okay. Now the area underneath this line, that is going to be the displacement. I'm so sorry. So this area is the displacement. Okay. And again, we could just skip right to finding the work, and then finding or finding a few other things. So there's a lot of things we could do. Let's go ahead. I forgot to mention that we are supposed to find the average force during the impulse. We didn't do that. I am so sorry. So the average force, in a way, this is almost like a statistical average force, times time. Okay. So what this means is the impulse over time is our average force, which that is going to be positive 8 kilogram meters per second divided by time is going to be, and that's a period of 6 seconds. So this is going to be this is not going to be a normal number. So it's going to be 8 divided by 6. So that's 1.333. So this is the average force. So this is going to be positive 1.33 newtons. Okay. So now we could actually find displacement really quick, just like we did the last problem. Okay. And so if you're a 111 student, I would, if I were you, I would find out, okay, again, there's no potential energies. You have initial kinetic energy plus work is equal to the final kinetic energy. I would use this to find work, which then I would go ahead and solve for displacement. Now, but since I have 121 students, we're going to go ahead and find the displacement right now. Okay, So to find this delta x right here, so that line, okay, it starts off at its initial, so we're creating a function of that velocity. So that line starts off at positive 5 meters per second times t, and the slope of that line is positive 4. So positive 4 over 6 meters per second over seconds. So this is going to be positive 2/3 meters per second squared t plus 5 meters per second. So now when we integrate to find displacement from 0 to 6 seconds, we're going to integrate this. So positive 2/3 meters per second squared t squared divided by 2 plus, that shouldn't have a t in there. A little sneaky. Plus 5t. Okay, so now let's go ahead and find the displacement here. So this is going to be from 0 to 6 seconds. So what we're going to get is 2 divided by 2. So 6 squared divided by 3. What is that? 18. So that's 18 meters. Plus 6 times 5 is going to be 30. So we're going to get a displacement of 42 meters. Okay, so that should be a displacement of positive 42 meters. I'm going to just write that right here. Displacement is equal to positive 42 meters. Okay, so back to this. If you're a 111 student, you should do it this way. I use the tools that are available to you. So this is going to be 1/2 2 kilograms times 5 meters per second that we're going to end up squaring plus work. And this would be 1/2, and this would be 2 kilograms times 9 meters per second that we're going to end up squaring. So this is going to be 25 joules plus work is going to be equal to 81 joules. So work is going to be equal to 81 joules minus 25 joules. And I don't know what that is. What is 81 minus 25? 56. So this is going to be 56. Whoops. That's going to be equal to 56 joules of work. Right there. Now again, work is equal, if you're a 121 student, you could just take in this delta x and multiply it by this, and you would have gotten 56. But let's just make sure. So work is equal to force times displacement. So work over force is equal to displacement. So this is going to be, work is 56 joules divided by 1.33 newtons. That is going to be equal to displacement, and hopefully it comes out to be 42. 56 times 1.33. I meant 56 divided by 1.33. 56 divided by 1.33. So 42. There's some rounding stuff going on, but this is 42 meters. Okay? So a lot of ways to do this problem. If you're 121 and you found that area right there, you could have taken the 1.33 newtons and multiply it by the displacement, which was 42 meters, and then you would have gotten 56 joules. So there's a lot of ways to do. So try to do what you can with your regular tools, but also try to learn some new things. Okay? Okay, let's go ahead and move on to a different problem. So this next problem we're going to do, it's a really interesting problem. I really like it. And it has to do with, it starts actually with energy, of all things. So in this problem, it says that you have a 2 kilogram ball dropped from a height of 2 meters. And it's going to impact the ground and lose about 80% of its initial energy during the bounce. The bounce is going to last for 0.02 seconds. And so what we're asked to do is figure out the maximum height after the bounce, figure out the velocities immediately before and after the bounce, the total impulse, the average force, and complete both this force versus time and velocity versus time graphs. Now you'll notice there are no numbers. We're going to have to put those in ourselves, just like we did in tutorials back in energy. Okay, so reading this problem, given that we have mass, which is 2 kilograms, we have an initial height of 2 meters, and we know we're going to lose 80% of our initial energy. Okay, so whatever our initial energy is, which looks like a ball which is dropped from rest, I'll put from rest, from a height of 8 meters, it's going to lose 80% of its initial energy. So that means we've got to subtract off 0.8 of its initial energy right there. So in this problem, we're going to have to start over here with our energy stuff and then work our way over to momentum, I think. Now, let's go ahead and do an energy problem. It starts from rest, but it has a height off the ground. No springs are touching it. In the end, it's going to reach a maximum height, where that means it's not moving at its maximum height and no springs are touching it. So here is our initial energy equation stuff before we start doing any interpretations. Now, this right here is the total initial energy, which we said we're going to lose 80% of that initial energy, which this is what it means, is our initial potential energy, we are going to lose 0.8 of that initial potential energy. And that is going to be equal to our final energy. So if the initial potential energy is 1, we're going to lose 80% of that energy. Okay? So just to make the math easier, if we look at this, we're going to go ahead and factor out this UGI, just to make the math easier. Okay? But this is what we're going to be actually doing, right? So you can do that. I kind of like to do things more methodical and as the problem is laid out. So what I'm going to do is I'm just going to actually start putting in numbers. So our initial, we have mass, gravity, and initial height minus 80% of that mass times gravity times initial height. And that's going to be equal to mass times gravity times final height. Okay? So at least doing it this way, I will know what the work is, where work is 0.8 times UGI. So that is how much energy is lost. Okay, now we're going to put in our numbers. So we got 2 kilograms times 9.8 meters per second squared times the initial height, which is 2 meters. Okay, 2 times 9.8 times 2, I think that is 39.2. So 2 times 9.8 times 2, 39.2. That's weird that I know that. And this is going to be 0.8 times 2 kilograms times 9.8 meters per second squared times 2 meters, and that is going to be equal to 2 kilograms times 9.8 meters per second squared times the final height that we need to solve for, because we're doing the maximum height after the bounce. So this is 39.2 joules. This is going to be 80% of 39.2, so 0.8 times 39.2. So that's 31.36. So we're going to lose 31.36 joules from the original 39.2. And that is equal to 2 times 9.8, 19.6 newtons. This is the weight of the object right here, so that's 19.6 newtons times the final height. A newton times a meter is a joule. Okay? So, in the end, this 39.2 minus 31.36 is 7.84. So 7.84 joules is the top part, and we're going to divide that by 19.6 newtons. So this part is just 7.84 joules, right? And that is going to be our final height that it gets to. So we're going to divide that by 19.6, which is 0.4. So 0.4 meters. So that's the maximum height that it bounces to after losing 80% of its initial energy. Okay? So we answer the very first part right here. Okay? Now let's figure out the velocities immediately before and after the bounce. Okay? Because that's going to help us figure out what impulse is. And since we have the time of the bounce, which is a fraction of a second, 0.02 seconds, we'll be able to figure out the average force, and that'll help us build our force versus time and velocity versus time graphs. So when a ball is first dropped from rest, its initial velocity is 0, but its height is greater than 0. When it drops down, right before it's hitting the ground, its velocity is greater than 0, but now its height is equal to 0. So this is before the bounce. So in other words, it has an initial kinetic energy. It has no initial kinetic energy. So if we're going to take this equation again, okay, so I'm going to write that out. The initial kinetic energy plus UGI plus USI, the spring energy, plus work, that's going to be equal to the final kinetic energy plus UGF plus USF. All right, so at the top right here, this is all happening before the bounce. So I'm going to write here before bounce. It has no initial kinetic energy, but it has a height. There are no springs. Since we're in free fall, right before it hits the ground, it's going to have a kinetic energy, but no height and no springs. Since it's in free fall, there is no work done either, right? So before the bounce, this is what we're going to have. Okay, and this is the velocity that it's hitting the ground right before the bounce. Okay, and I should write mghi equals 1/2 mvi squared. So, or 1/2 mv squared. So this is the velocity right before it hits the bounce, hits the ground. So the masses cancel out. You get 2ghi square root, and that's equal to the initial velocity. So when we pop in this is going to be 2 times 9.8 meters per second times 2 meters. This is going to be the square root of 39.2 meters squared per second squared. And I don't know what that is. That sounds like it's close to 8. So 39.2, or maybe close to 6. And then we're going to square root that 39.2. 6.26. So right before hitting the floor, it's traveling at 6.26 meters per second. So that's the initial velocity. Okay, so we found the height. We found the initial velocity right before hitting the floor. Now let's figure out what the velocity is after the bounce. So now, after the bounce, it starts here. So it's doing the opposite of this. And it has a velocity greater than 0, but its height is equal to 0. And so now this one is traveling down. This one is going to be traveling upwards. And by the way, this is its speed, its actual velocity. I'm sorry, going back to this. Since it's moving downwards, we're going to have to add in a negative to this, right? Because it's traveling down at negative 6.26. So we're artificially adding that negative number. Okay, that's its velocity right before impact. It's traveling down at 6.26 meters per second. So we solved this for 6.26 meters per second, and then we added in that negative. Okay, after the impact, it's going to have an initial velocity upwards, and then it's going to reach its maximum height, where its height is now greater than 0, but at your maximum height, your velocity is equal to 0. So, starting with our equation, it's K final plus U sub G final plus U sub S F. Now, when it starts here leaving the ground, so it's fully left the ground, now it's just moving upwards, its height is 0, no springs are touching it. When it reaches its maximum height, it's not going to be moving, it will have potential energy due to gravity, and no springs are touching it. Since it's in free fall during this last part, there is going to be no work. So what we're going to have is we're going to have an initial kinetic energy, which is going to be equal to a potential energy. So this is going to be 1/2 mv squared. So this is what we're going to be solving for. That's the velocity right before leaving the ground. Okay. Well, right after leaving the ground. And that's equal to the maximum height it gets to, which is going to be mgh. And we know h up here, which is 0.4. The masses are going to cancel out, and so that velocity that it's leaving the ground at is going to be equal to 2 GH, which is this final height it gets to, which is the square root of 2 times 9.8 meters per second squared times a height of 0.4 meters. What is that? That's about 20, 0.4 square root of that. That's close to 3, I think. Let's find out. So 9.8 times 2 times 0.4. 7.84, and we're going to square root that. 2.8. That's pretty close. So now, leaving the floor is going to be 2.8 meters per second. So this is the velocity, and that's going to be positive, that is leaving the floor. So this is after impact. And this is before impact. Okay. Well, now we have enough information where we could actually figure out J and everything, right? So we have the momentum before impact. We have the velocity for the momentum after the impact. And we have the time of the impact. So we could figure out a lot of things. So the initial velocity before impact plus J, that's going to be equal to the momentum after the impact. Okay, so this is going to be 2 kilograms times the velocity before impact, which is going to be negative 6.26. So negative 6.26 meters per second. Again, I'm going to emphasize that that's traveling downwards before the impact, plus J, put little vectors on these, and this is going to be equal to 2 kilograms times 2.8 meters per second, which is after the impact. So let's go ahead and get our calculator and start calculating. So 6.26 negative times 2. So negative 12.52. So this is negative 12.52 kilogram meters per second plus J, and that is going to be equal to 2.8 times 2. 5.6. So positive 5.6 kilogram meter per second. So J is, we're going to add that. We got our 5.6 kilogram meter per second. And now we're going to add our 12.52 kilogram meter per second. Okay. I'm going to erase this. This guy is encroaching. I'm going to do some other things here too. I'm going to move some things over so I have some room. Hold on a second. So I just moved this over a little bit. And now, with our calculator, 12.52 plus 5.6. That is the impulse. 18.12. And that's also the change in momentum. So positive 18.12. And that's kilogram meter per second, which is also a Newton second. So let's write that so that's legible. This is a kilogram meter per second, but again, this is just a Newton times a second. So with that, since J is going to be equal to the average force times the change in time, well, that right there is, so we're going to have, let's compute the average force. So we figured out J. That's one of the things that we had to solve for. Now we're going to multiply that times our 0.02 second time of impact, and that's going to be equal to 18.12 Newton seconds. So the average force we're going to take that positive 18.12 Newton seconds and divide it by 0.02 seconds. So the average force, let's go ahead and figure that out. (906). So this is going to be 906 newtons. Okay. Well, now we have everything we need to complete the force versus velocity stuff, right? Let's do the force one first. That's 906 newtons acting over a period of 0.02 seconds. So you can put this anywhere. You don't have to number the scale if you don't want to. So I'm just going to call this 906 newtons. That's positive. So if that's 906, this would be negative 906. But this force is going to be upwards because the ground, if a ball's coming down, it's got to push it upwards to bring it to a stop and then push it upwards again to send it back out. And this is over a period of 0.02 seconds. So this average force, which is average forces are constant forces, is going to look like this. Okay. Now the area underneath this, that is going to be the impulse. Okay. So 906 times 0.02 is going to be 18.12. Now, for the change in velocity, it's traveling down at negative 6.26. So I'm going to call this negative 6.26. So it starts off at traveling at negative 6.26 meters per second downwards. And over the period of 0.02 seconds, it's going to wind up at 2.8, positive 2.8 meters per second. So if that's, so this will be like positive 6.26. And right in the middle is going to be positive 2.8. And in the middle here is going to be negative 2.8. Obviously it's not to scale, but here is what this guy's change in velocity is going to look like. And that's how to do this problem. This problem that I did, obviously it's not like the one you're going to experience, but I wanted to show you what to do when you have a longer, more involved problem, okay? And again, these tutorials are not just about completing, these examples are not just about completing the tutorials that I'm going to assign you. It's also part of the lecture, okay? All right, let's move on. So now, so this problem is where, just going back to it for a moment, this problem is where our lecture ends for Physics 111 students. Physics 121 students, we have 2 more to do, okay? So if you're in Physics 111, you can stop right here. Physics 121, well, we have a little bit more to do, okay? So suppose you're given a 10 kilogram object that is originally not moving, but then it receives a force, as a function of time modeled with the following equation. So here's the equation, and here's what that force looks like graphically. What I did to create this is I just put this function into Excel, and then I put in numbers starting at 0, 0.1, 0.2, all the way up to a maximum, just really, really far. So I put in times of starting with 0, 0.1, 0.2, and so on and so forth, going all the way until I saw that force function reached 0 again. So at 0, this function is equal to 0. And then when that function reached 0 again, it happened to be at 4 seconds. And so I just graphed that. And this is an Excel graph right here. Okay? Now, and impulses do look a little bit like this, right? It's not a perfect normal curve because it would have a rounded edge at the bottom, but this is a pretty good similarity of what you would experience with an impulse, okay? And so here's the force that you're given, okay? So in this problem, we're supposed to figure out the final velocity, the maximum force of the gust, and the average force from 0 to 4 seconds, and the displacement of the object during the applied force. Again, that displacement we can get a lot of different ways, okay? However, let's just go ahead and get started. So our first task is to figure out the impulse right here, right? Because this area underneath that curve, we have the initial velocity, which is going to be equal to 0, plus impulse, which is going to be equal to the final momentum, right? Well, this is just 0. So impulse is going to be equal to our 10 kilograms times the final velocity, right? So in order to find the final velocity, we need to figure out impulse. Well, given a graph of force versus time, well, how do you find impulse? Well, that's the area underneath this line. So let's figure that out. So what we're going to do is figure out the area underneath this line, which is described by this function. So I'm going to just write the function right here. Maybe I'm going to write it over here. Final velocity, f of t, is going to be equal to negative 25 t squared plus 100 t. Now what we're going to have to do is, to get impulse, we're going to have to integrate that function with respect to time from 0 seconds to 4 seconds, okay? We have to do it this way. I do not know any other way to do this problem. You have to use calculus to do it, okay? So this function that we have, 0 to 4 seconds, which is going to be negative 25 t squared plus 100 t dt. All right? So when we integrate this, this is going to be, this negative 25 is going to stay there. And what we're going to get is we have a t squared, so that's going to become t to the third divided by 3. And this is going to be plus 100, and we have a t in this equation, so that's going to be t squared divided by 2. And that'll be going from 0 seconds to 4 seconds. Okay. So this impulse that we're going to get is going to be negative 25 divided by 3, and we're going to go 4 seconds minus 0 seconds, and we're going to cube that, and then we're going to add to that 100 divided by 2. I just took the 2 and brought it to the front, and that's going to be 4 seconds minus 0 seconds squared. Let's plop some stuff in the calculator. So 4 seconds minus 0 seconds is 4. And then we're going to go ahead and cube that. So 4 times 4 times 4 equals 64. Times 25, that is negative, equals, and we're going to divide that by 3. So negative 533.333. So that's the first part. 0.33, and that's Newton seconds. And then we're going to add to that 16 times 100 divided by 2, or just 16 times 50. Let's do 16 times 50. 16 times 50. So that's 800. And that's 800 Newton seconds. By the way, this is a Newton, this whole thing is a Newton. That's what's describing that function. So our overall impulse, after everything is done, is going to be minus 533.33, which is going to be 266.67. So positive 266.67 Newton seconds. Okay, and so that is the area underneath that line. So we're going to have to plug that in over here. So now we know that is positive 266.67 Newton seconds equals 10 kilograms V final. So our final velocity after this gust of wind, which apparently is really huge, and I'm going to zoom in over here and I'm going to fix this. This looks terrible. 266.67. So positive 266.67 Newton seconds divided by 10 kilograms is going to be 26.67 meters per second. Positive. Right there. So that's the final velocity after the gust. Okay. Now, the maximum force of the gust. All right. So this one we have to kind of think for a second. All right. Now, there's a lot of ways you could do this. This is a parabola, and if its maximum time is 4 seconds, well, it's going to reach its maximum height at 2 seconds, right? So right here, you could see if we draw a tangent to the line at 2 seconds, it's reached its maximum height right there. Let's try this again, and I'm going to so it's reached its maximum height right there. At 2 seconds, okay? Which looks like it's 100, okay? There's a lot of ways to do it to figure out that maximum force of the gust. Okay, so the maximum force of the gust since we have a really convenient parabola, we're going to do it two different ways, okay? We're going to take this function, and since we know the time, 2 seconds, that it reaches its maximum force, since we have a nice smooth parabola where we know the minimum and maximum, divide that by 2, and that is the force at the maximum point. So then we're just going to put in 2 seconds here. So this is going to be negative 25 times 2 seconds that we're going to square plus 100 times 2 seconds. So let's figure that out. So 25, so 2 seconds squared, that is going to be 4. So 4 times 25, negative 25, that is going to be, why do I have my calculator up? 4 times 25, so that's negative 100 newtons, plus 2 times 100, so that's going to be 200 newtons. And so the maximum force, which occurs at 2 seconds, is going to be 100 newtons. Okay? Another way you could figure this out, okay, is if you notice the slope of this line is 0. Okay, so we know in a parabola, and it doesn't continue on, that it reaches, so notice at that maximum height, that slope is 0. Okay, and that's really important. Okay, so here we have our function, okay, which is negative 25 t squared plus 100 t. Okay, and here's what I'm saying. If we know when it reaches that maximum slope, and that's a derivative, by the way, we take that function, we take the derivative of that function with respect to time, and we set it equal to 0. So in other words, we're going to take this function of negative 25 t squared plus 100 t, and we're going to take that derivative with respect to time, and whatever that works out to be, that's a slope, and we're going to set that equal to 0. Okay, so in this problem, we have the convenience of knowing that 4 is the maximum time and 0 is the minimum time. Divide that difference by 2, and you know what the maximum height is. But in problems like this over here, well, you've got a problem. You don't know that time right here. It's not falling directly on 8. So if you wanted to find the maximum positive force here, well, now you have to do this. Now you have to take the derivative with respect to time. Okay? If you don't know the time of all that, you have to take that derivative. Okay? So I want to set you up so that you know what to do in specific situations when you don't know the total time, and in this case where you have to figure it out. So taking the derivative of this with respect to time, we're going to take this, which is going to be negative 25. I'm just going to bring that to the front. This is going to be times 2 t to the 2 minus 1. It's been a while since we've done derivatives, so I'm kind of doing a little bit of a review. So this should be t to the 2 minus 1. We're subtracting off 1, plus 100, and that's going to be, we got to bring, this is t to the first, so we're going to multiply that by 1, and then, so we're going to multiply that by 1, and then we're going to take t to the 1 minus 1, which is just 1. This whole thing is t to the 1 minus 1 is just 1. Okay, So this is going to end up being 0, and then you have negative 25, so that's going to be negative 50, and that's times t, plus 100, and this whole thing, that's 1 times t, 1 minus 1 is 1, so this is plus 100. Okay. And so if we do it this way, we're going to take that 50t and add it to the other side, and that gets us that sets us equal to 100. So this tells us that when the slope is 0, that occurs at t is equal to 2 seconds. So once you have that, then you plug that 2 seconds in right here. To our original equation. And so by doing that, so now once you figured out when that occurs, where that slope is 0, then what you have is, then you could plug that back into here. Okay? So that's how you get the maximum force of the gust. There's 2 ways to do that. Okay? And since it's nice and convenient, and we know it's from 0 to 4 seconds, and you could see at that at that parabolic or that hyperbola, the parabola. Oh, good Lord, words, Jim. Anyways, that is going to be the maximum force. Okay. Now, good news is to find the average force from 0 to 4 seconds. That's going to be pretty simple. Okay. So I'm going to move this. I'm going to do a little landscaping here on my problem. Hold on one moment. So I just moved all those equations right over here. And again, we found the initial velocity right here. We found the maximum force of the gust. And the initial velocity. And now we need to figure out the average force from 0 to 4 seconds. Okay? Well, the good news is we figured out what the impulse was. So right over here, if impulse is equal to force, which is the average force, times time, well, that impulse, which is so to figure out the average force, what we're going to do is just take the impulse that we figured out and divide it by the period of time, which we know is 4 seconds. And that is the average force. So that is going to be positive 266.67 Newton seconds divided by 4 seconds. And that is the average force. Okay, and let's go ahead and find that out. 266.67 divided by 4 equals 66.67. So the average force is 66.67. So that's the average force, and that's newtons. And I'm going to take this and I'm going to scooch that over right over here. Okay, so that's how we figure out that average force. Now to get our displacement, you could graph the initial velocity versus final velocity, which is going to be a triangle, and then integrate that velocity versus time function and get displacement there. I think it's quicker and easier to just do it the practical way, is using energy. Okay, so our initial kinetic energy, it's not moving initially. It's not changing height. There is no potential energies. In the end, it is moving and there are no potential energies. So we have work is equal to the final kinetic energy. So this work function is going to be equal to 1/2 the mass, which is 10 kilograms, times the velocity, which is going to be 26.67 meters per second, which we're going to square. Times 26.67 times 5 kilograms divided by 2 is 5. So we're going to just multiply that by 5. So 3556.44. So 3556.44. And that is the work done. Well, work is going to be equal to the average force times delta x. So work over the average force is equal to delta x. And where work is equal to 3556.44 joules over an average force, which is positive 66.67 newtons, that's delta x. So we're going to divide this by 66.67, which is 53.34. And that will be meters, and that is delta x. So I wanted to put this problem on here for you guys where it makes you have to do quite a bit. You have to learn, you have to do quite a bit to understand this. Okay? So this is a good problem to do. It teaches you a lot of things. Okay? And so again, it's probably safest for you, since you're 121 students, to if you know the times, divide that by 2, and that will be the maximum force. As long as this initial force is 0 and that final force is 0, you could go ahead and do that. But if you don't know that, where its maximum is, you have to take the differential and set it equal to 0 to find the maximum slope, because that's where it's reached its maximum slope. And then that'll tell you the time that it is reaching that maximum slope of 0. And then plug that time back into your original function, and that tells you the maximum force of the gust. Okay? All right. Finally, last problem. Okay? And I apologize for the length of this video, but I hope you're learning quite a bit. All right. In this last problem, you have a 100 kilogram sport ball player, so somebody where weighs about 220 pounds, is moving to the right at 4 meters per second, where a force as a function of time is being applied to them by an opposing player modeled with this force, which looks like this. And they're doing it over a period of 10 seconds. Okay? So the person's moving to the right. This other player is trying to push them, which initially is pushing them to the right, and then begins to push them to the left. Okay? So we want to know what the average force of that push is, or pull. So we need to know their final velocity after this happens. We want to figure out what their average force is from 0 to 10 seconds, and then their displacement of the player during the push. So this problem is similar to the other problem. Okay? So similar to the other problem. So here is what we're going to do. Let's start off with momentum. Okay. Since we have mass, we have initial speed, and we're given a force and time, that is leading us to figuring out that final velocity, right? So the initial momentum of the sport ball player plus impulse, that's going to be equal to the final momentum of the player. Okay, so this is going to be 100 kilograms times 4 meters per second, which is positive, so they're moving to the right, plus whatever the impulse is, which is the area underneath this line, okay, which we'll get into in a second, and that's equal to 100 kilograms times the final velocity. Okay, so that impulse is going to be an interesting problem, okay, because you have two parts to this impulse, okay. You have this initial part, which starts out above that line right here. So this is the initial part, but then it drops below that line and then this area is subtracting from that top area. Now, the best way to do this problem is to find impulse, okay, which we're going to do here for now, is where the impulse, again, is going to be the integral of this equation right here, from 0 to 10 seconds. So we're just going to hop right into it. So this equation is -1/2 t squared plus 4t dt. Okay, so really similar to the last problem. So this is going to take the -1/2 to the front, and then we're going to have t to the third over 3 plus 4, and that's going to be t squared divided by 2, and that's from 0 to 10 seconds. And so I'm going to hurry this one up. So we're going to put in 10 minus 0, which is going to be 10. So this t cubed. So this is going to be 10 to the third power divided by 6. So 10 times 10 times 10. So that's 1,000 divided by 6. 166.67. So this is going to be -166.67 Newton seconds. And that's going to be plus 4 divided by 2, which is 2 times 10 squared. So that's going to be 400 Newton seconds. So the impulse is going to be 400 minus 66.67, which is 233.33. Newton seconds. And so you could see from this problem, this blue part is this 400 Newton seconds. And the red part is going to be this part right here. Okay. I'm pretty sure that's the case, but so now we could just plug that right in right here to find the final velocity. So this is going to be 400 kilogram meters per second plus 233.33 and Newton seconds is also kilogram meters per second, since we're going to convert this to a momentum, and it'll look better, kilogram meters per second, and that's going to be equal to 100 kilograms V final. So this is going to be 633.33 kilogram meter per second that we're going to divide by 100 kilograms, and that is going to be our final velocity, which is 63.33 meters per second, which is scary fast. This person must have been smashed really hard. I'm not sure this problem is realistic. All right. Now that we have that, let's get the average force. So since we have impulse again is average force times the change in time. And that average force would be kind of a constant. So if we take, to find delta t, if we take that impulse and divide it by, nope, we want to find average force, sorry. Find average force. We're going to take impulse and divide it by time. This is going to then be the impulse, which is positive 233.33 kilogram meter per second that we're going to divide by 10 seconds. So the average force is going to work out to be positive 23.33 newtons. Okay? So that's the average force. Now, to find displacement, all right, I'm going to do this. I'm going to grab this guy. Just doing a little bit of landscaping. All right. That way when we look out, we understand where we're going. Okay, so now let's go ahead and let's figure out the displacement during the shove. Okay, so this player is on the ground. He's just moving in the x direction. So they have an initial kinetic energy. Their potential energy isn't changing. They do have a final kinetic energy, but their potential energy isn't changing. So we have an initial kinetic energy plus work is going to be equal to our final kinetic energy. So this is going to be 1/2 mv initial squared, and our initial velocity is 4 meters per second, plus work, which is going to be the average force, times delta x, and we're going to assume that that's a constant, right? Average force is a constant force. That's going to be equal to 1/2 the mass times the final velocity squared, which we figured out was down here. So when we do our algebra on this, we're going to take this onto the other side, and we're going to subtract it, and then we're going to divide both sides by this. Right? And I'm just doing this for the sake of time. So F average times delta x. We're going to take our, you know what? I'm going to plug in numbers first. Let's do this. Let's just be teaching you. Okay, so let's plug in our numbers. So we got 1/2 times 100 kilograms times 4 meters per second squared that we're going to square. That average force that we figured out, that was 23.33 newtons. Times the displacement, which is going to be equal to the final kinetic energy, which is going to be 100 kilograms times 63.33 meters per second that we're going to square. Okay, so 100, so this is the initial energy is going to be 4 squared, which is 16, times 100 divided by 2, which is 50. So that's going to be 800. So this is just 800 joules plus 23.33 newtons times delta x. This 63.33, that's going to be a huge number. 63.33 times 63.33 times 100 divided by 2, which is just 50. 200,000. And this person's going to die, probably. So 200, 534.45. 534.45 joules. Yeah, that's a lot. Okay, I'm going to make sure that 5 looks like a 5. That's a huge amount, which we're going to then subtract off 800. So minus an itsy bitsy 800. And we're going to divide that by 23.33. So their displacement is 8,561.27 meters. I'm pretty sure 8,561.27 meters. Okay, this ceases to be a sport ball game and is more like a nomadic journey. Really, it's going to take forever to go that far. Maybe I'm going to switch the theme of this to, I don't know, a car driving. Anyways, a cart driving. That is examples of how to do impulse problems for 6.0 Introduction Momentum Impulse. Again, this is another lecture, so I hope you learned a lot. Thank you very much. Bye.